In this example, we examine connected pipes, loaded connected pipes. Okay, this is a steel pipe with an outside diameter of 95 millimeter, inside diameter of 85 millimeter. Supports loads shown in the figure below. Okay, here we have 3 loads. Here is a PY and PZ and PX. Okay, here are the directions of the 3 axes. The X, here is the Y, and Z direction here. So determine the shear stresses on the surface of the pipe at point K, okay, and determine the normal stresses on the surface of the pipe at point K. Point K is here. Okay. Then the dimension has been given here. So you can see the point K is here if you cut the pipe from here through point K, and you can see which axis is the axial direction. Is that X, is that Y, or Z? Right, so obviously the Z is the axial direction, right? So using the methods we just introduced, you can, first of all, in the first step, you determine the internal forces based on the external loading. Okay, so that is our first step. Determine internal forces. Okay, we got the table. So here, as we just analyzed, here you have X, Y, Z, and Z is the axial direction. So the internal forces along X and Y direction through point K will be shear forces, right? So here we will have Vx, Vy, and Fz. And so at the same time, you have Mx, My, and Tz, right? If it's respected to z-axis, then it will be a torque, right? Otherwise, with respect to x and y, there will be bending moment. Let's see here, we have 3 external loadings, and those are Px, Py, and Pz. Right? Px, Py, and Pz. Okay, so here let's look at Vx. Will Px make any Vx? Yes, they are both in x direction. Look at here, the Px is in the opposite direction as the positive direction of x. So here the Px will be a negative value. The Px is 14 kilonewton, so it will be negative 14,000 Newton. Okay, then the Py and Pz will not have any components along x direction, right? So in the same way, the Vy, Px will not any Vy, right? Only Py make Vy. The Py is 10 kilonewton. Let's look at the direction. Py is here, and y is pointing upward. So again, it's a negative 10,000 Newton. In the same way, the Fz will just equal negative Pz, right? So negative 7,000 Newton. Then let's examine Mx. So will Px make any Mx? Well, no, obviously no, right? Since they are parallel. So here it's a 0. So it's a parallel. Right. How about Py? Will Py make any bending moment x-axis. Py is here. Okay, Py is here. So x is there. Right? Will Py make a bending moment mx? Yes. What is the arm? The arm is a, right? So Py times a. How about Pz? Will Pz make any bending moment about x-axis? Yes. So what is the arm? The arm is b. Right? The arm is b. So here is Pz times b. So do they have the same? Do they have the same direction, the same sign? Okay, they have different signs. Okay, just note there, they have different signs. It's a PYA. PYA will be in this direction, and the PYZ, PZ times B will be in the opposite direction, right? But does this matter? If you are just examining point K, right? So does this matter? If you really need to determine mx, you do need to take care of them. Okay, take care of them. They have different signs. So let's note here. Different signs. So you will see that if you need to determine the normal stresses later at the point H, so you need to calculate this. You need to solve this out, right? But we're calculating the bending moment at the point K, right? Since if you're calculating the normal stress induced by mx, what is the y value of point K? It's 0, right? So it doesn't matter. You don't need this mx at all, right? So we do not need to solve it out, right? Because y will be 0. Okay. Then how about my? The my, does px make any my? Yes. So what is the arm? It's a, right? So here you get a px times a. How about py? Of course, no. Right? Py is parallel. Py is parallel with the y-axis, so it will not make any bending moment. Then pz. Would pz make a bending moment my? No, because arm is 0. Okay. So in the end, we can examine tz, like the torsion. So here, how about px? Will px make a tz with respect to z-axis? Yes. So what is the arm? The arm here with respect to z-axis will be b, right? So here will be px times b. Then how about py? No, py is arm equals 0. How about pz? No. Okay, it's parallel. Okay, so here we have finished the analysis of the internal forces. Then the second step, we normally need to determine their the section properties. Here we may need A and I, right? So what is the A? Since you know the outside diameter and the inside diameter, so the A will be pi over 4 95 square minus 85 square. Okay, so here you get 1414 square millimeter. Then the I will be pi over 64, 95 to the fourth minus 85 to the fourth. Okay, you will get 1.436 million mm to the fourth. Okay, then in the third step, we can analyze let's do normal stress first. Okay. So step 3, to calculate normal stress. Normal stress at point K. So as we just analyzed, you will have a normal stress induced by axial loads. Okay, we have one axial load that is Fy, right, negative 7,000 Fz over A. That is negative 7,000 Newton over A is 1414. Okay, 1414 square millimeter. And the result will be directly MPa, right? It will be negative 4.95 MPa. Then you have the second component due to bending moment. That is mx y over I. Right, the mx, we didn't combine them because we said it doesn't matter, and so we do not need it at all because y equals 0. Right? When you consider mx, so the k will be on the plane, the neutral plane, right? So the y equals 0. So we don't need the number at all. So this will be 0 since y equals 0. Okay, so how about the third component? That is due to my. So my has only one part, is the px times a. So my times y value. And here, if you calculate the bending stress at point K due to my, so just here is y. So my, then the y value, the distance from point K to the neutral axis, will be, since it's on the surface, on the bottom or the top, right? So there will be c. We'll use the c value over I. Okay. So my is px times a. Okay, px times a times c over I. Okay, so that is 14,000 times the a value is 450. 450 times c. The c is just half of the outside diameter, right? So that is 95 over 2 over 1.436 times 1 million. So here you will get 208.39 MPa. The question, is this a positive or negative stress? Point K here, right? So let's draw this. The point K is here, right? The y-axis is here. And the px direction is in that direction, px, right? So the bending moment, under this bending moment, will point K be stretched or compressed? Will be stretched, right? So what is the sign of this result of this bending stress? Positive, right? Here you have positive stress. And the sigma 1 is a negative, right? Then the overall stress at the point K will be just a combination of these three normal stress values. So you have negative 4.95 plus 0 plus 208.39. You get 204 times 44. MPa. Okay, so that is the normal stress at point K. Okay, then the fourth part, we will examine the shear stress. The shear stress at point K. Right. So how many components do you think we will have for this shear stress? So first of all, let's look at here. You will have a okay. We have three possibilities, right, to make shear stresses. Right. The first one is Vx. The second is Vy, and the third will be what? The torque here, right? So we have a torque. So in the previous examples, we didn't involve any torque, right? But here we have a torque. We have two shear forces and one torque. Okay, all of the three things can make shear stresses at point K. Okay, so here is the cross section. Again, just look at this cross section. Let's draw it again. Okay, so here is the cross section, and your point K is here, and you have the x direction. This is x. You have the y direction. So let's look at this. If you have Vx, what is the tau? That can be induced by Vx. If you have Vx, then you cut it, you cut the area, you will cut it from here, right? So the area will be 0, right? So area will be 0, then Q is 0, right? So since tau equals what? Tau equals VQ over IT. So your tau will be 0, right? The tau will be 0. Here the first component, tau 1 will be 0. Then the second possibility, because of the Vy, the shear force along y direction. Okay. So here, because of this, you will need to cut it from here. So you got a area, since the shear will be the shear is downward, right? The Py is downward. Okay, you cut it from here, so you will need to calculate the A, D, and Q. Then you can determine the tau 2. And due to Tz, tau 3 equals what? Equals what? Equals Tc over J, right? So you can calculate this. Then let's look at examine the directions of them. Okay, look at the tau 2. Tau 2 here, the equation would be VQ over IT, right? So since the Vy is downward, so the tau 2 will be downward, right? So this is the direction, this will be downward. So how about the T3, the tau 3? The tau 3, so look at the direction of the torque. Direction of the torque. Tz is what is px times b, right? Tz is px times b. So look at px. The px is here, right? So induced by the px times b, so the direction of the torque will be, right? This is the Tz direction. So the induced shear stress tau 3 at point K will be upward. Right? So if you get these two values, add them together, you will also need to consider their signs, right? Since they will be in different directions, so have opposite signs. Okay. So I will not give detailed solutions to stimulate you to go back to check the previous chapters. This equation and this equation, okay, how to determine those values, the Q and the tau, and how to use the previous torsion equations. Okay, this will be in the review stage. You just go back to check them, but in the exams, it's not likely that we'll test this kind of complicated combinations. But it's key, it's essential to know them separately, like how to consider the torque to determine the shear stress, and how to consider the V to determine a shear stress.